Hello, everybody. I'm very happy to host today someone very special to me. So today I will present part of my PhD. And someone's coming. Okay. So today my name is Elad, and today I'm going to talk about part of my PhD. And during my PhD, during my PhD, I mainly focused on two projects. The first one we called model extraction, in which we managed to show an efficient algorithm that can provably extract the exact parameters of 2 and 3 layer neural networks. And the second part was to obtain sublinear generalization bounds for neural networks. And this is what I'm going to talk with you today. And usually when people come here, they starting by introducing the problem. And I'm going to do something different. I'm going to start with introducing you with the solution. And we are calling the solution ApproximateDescription Length, or ADL. And I'll give you some intuition, and then we'll go to definition. But before all of this, let's start with, of course, definitions. Calibrated X will be our domain. It will assume it is the dimensional box. H will be our hypothesis class, which is real valued functions. So usually we consider H to be binary, either 0 and 1 or -1 and 1. But here we are extending it to be real functions. Hello, you missed only the definitions. And X will be our samplet, which uses M sample. So actually we'll mostly use M, not S, but M will be our sample size, and S will be the sample set randomly chosen by some distribution. And the restriction of H to S will be denoted by H subscript S, which is just the restriction of H to S. And we'll use two norms, the spectral norms and the Frobenius norm, in which we denote with the subscript F. Okay, so our learning scheme that we are going to talk today is some extension of pack learning to real functions. So hypothesis class, real value hypothesis class is learnable with margin of 1 if there is some sample complexity M, such that for every epsilon and delta and distribution with probability 1 minus delta, you know the over M examples drawn ID from this distribution, and M, of course, is a function of epsilon and delta. When we run the algorithm, it produces an hypothesis that it approximately correct. So approximately is the function epsilon. So we want to approximate our correctness by bound our generalization by epsilon, and we want to allow our function to be as far from the real by at most 1. Okay, so this is to be correct. This is why we call it a margin by 1. And when it's bigger than 1, then we are incorrect. And I can also write the grade agnostic case. And what we are going to talk about here, so we'll fix delta. We assume delta is fixed. And we focus on the relation between the generalization error epsilon and the sample complexity M, how they interact with each other. Yeah. Where?
Minimum over half. The agnostic.
Oh yeah. This one should be F. Yeah. All right, thank you. Okay. And some very known results are for finite hypothesis class. So for finite hypothesis class, we know that the generalization error squared, epsilon squared, is degrading with log the number of functions. So this is like first known result. But what if age is not finite? What is infinite? So sometimes we can use an approach which is called the coloring number, and the idea is if we could cover our class with balls of radius gamma, so this is called the gamma cover, and if you could do that, then of course each function will be gamma close to one of those covering, one of those balls, and if the number of balls is finite. And will be the smallest such set that cover the entire class. So if this covering is finite, then we can actually replace age with the covering number itself. Okay, so this is the basic intuition about covering, and assume before I'm going to talk about approximate description length, assume that I can encode each ball with some k bits. So if I can do that, then we have at most 2 to the power of k hypotheses, which means we can replace the covering number with k, with the number of bits. So this is description length approach. And what I'm going to introduce today is an approximate description length, or an ADL. And the idea is that we allow varying the number of bits for each hypothesis. Some will be less than k, some will be more than k, but if we can bound the average number of bits for every hypothesis, and by average, I'll show you better definition later, but if we can do that, then we still replace the generalization error by this number of bits. So this is the intuition, and note tilde O, it's an order without logarithmic terms. Okay, so not just constant factors, also logarithmic factors. And this will be tilde. And so this is the idea of approximate description length is what I'm going to explain today. So let's start with by 3 definitions. So the first one is a sigma estimator. So what is a sigma estimator? For a function h, a sigma estimator is a random variable, is an unbiased estimator for this function. And with bounded variance by sigma squared. But note that we allow h to be dimensional valid function, not just every valid function to not just R, but R B. So we want to bound the variance in every direction. So that's why we are multiplying it by a unit norm vector. Okay, so a sigma estimator in simple words is just an unbiased estimator with bounded variance on every direction. Okay. The second definition, which will be less formal, but to give the idea about what is a compressor. So assume first that every function of our class has a sigma estimator that is an unbiased estimator with bounded variance. And there exist 2 special functions, len and enc, such that every event of every estimator, because remember, an estimator is a random variable. So for each event, we have a function len that will give us a number, and enc will encode uniquely this event with number of bits that is the length of len. Okay, so every function has a unique encoding, but in a varying number of the code, where then is the control of how many bits it will get. So the 3 functions, phi, enc, and len, is called sigma and compressor. If, of course, it's sigma estimators open and the expected value of the expected number of bits is at most n, for every function, for every class. Sorry, for every hypothesis. Okay? So the idea is clear. We want to bound the expected number of bits for each hypothesis. Yes? Okay, great. And the last definition, this one I brought again, so you can view. And the last definition, we say that the class has an approximate description length of n, which can be also a function of m, the number of samples, if it exists to one n compressor. So if there is, for every function, we can give an unbiased estimator with variance of 1 that we can encode with an average number of at most 10 bits. Okay, this is what we mean by an ADL. Okay, variance 1 and back bits. Questions in now? Yeah.
How similar is it to like the ideas from the information theory of coding random variables, stuff like that?
So I'm guessing it's pretty similar, but I'm not really know this field too much. I'm guessing it's a bit similar, except that it depends. Sometimes I think as they required prefix 3 code or something like this, actually we can assume this or not because it's the same asymptotic result. What? Yeah, okay. We read it later, but I'm not too much know this field. I'm guessing it should be similar somewhat. ב-NDL בדרך כלל מאפשרים להיפותזות שונות להיות מיוצגות על ידי תיאור באורך שונה, האם הגדרות כאן מאפשרות Okay, so the difference between description length and to approximate description length. So in description length, we create a different set of classes with increasing amount of description. So each class, like you have a class with increasing size for each description, and here we have only one class, and we want that the average number of bits will be bounded. I don't know if I was clear. Let me rephrase it. So description length is just an infinite number of classes. Each one grows over the other, where we allow the description to grow, and it's only one class that we bound by an approximate number of values. Yeah, was it clear enough? Okay. 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 So our first result is that ADL can be a proxy for vulnerability for bounding the generalization error. And we will show that by reduction to covering number. And some side notes as for the other question, for the other direction, whether ADL can be lower bound for vulnerability as this is, which dimension for binary classification. So it's not well known, and there are some first results by Danielitz and Katzenhandler that show some nice things, but we will not get into that. So our first result is that given a class that is approximate description length, a class of real valued functions that have an approximate length n, then we can bound the number of the covering number, the low covering number of any radius of any gamma cover using order of n divided by gamma squared bits of ADL. No, sorry, evolve. and will be our ADL. So this is our first claim. And the second claim is that if we allow age to be d-dimensional real-valued functions, then we can bound the log number, the covering number, by the same order, except for adding a logarithmic term, which is also a function of the number of samples. We couldn't avoid it. Maybe there is a tighter bound to that, but so this is the result. And let's prove at least for the one-dimensional case. So how will we bound it? We will show a covering that is made due to our ADL. So remember, we need to find a covering of size gamma, and we want to upper bound the number of those for this cover. So we'll do it in 2 steps. So first, assume some function age. We know that ADL we know that age as an ADL second, which means there are one estimator for every function. So an estimator is a random variable, so we can actually create k such estimators, independent estimator for the same function h. And by averaging them, we get that the expected value of the average doesn't change, but the variance of the average is decreased by a factor of k. So we managed to create, by averaging k IID1 estimators, 1 over squared k estimator. So it is nice because we managed to reduce the variance, but in what cost? I mean, what is the catch here? If we can only reduce the variance more and more, it should be some cost. Yeah, the description increased. We need more bits. We need n time more bits to encode the function h tilde. Okay, so this is our trade-off: lower variance, higher number of bits. So for the second case, the second step, sorry, let's assume k is 1 over gamma squared, and therefore our function is a gamma estimator with n divided by gamma squared bits. And the second claim is more technical. It's just using concentration measures, Markov of the gang. But remember that what we want to show that there is a covering of size order of n divided by gamma squared. So the following probability, what does it mean? It means the following. We want to bound the probability to lower bound the probability that this function h is far by at most gamma from our function. So this is the first part that we want to indeed be gamma cover, and the second part is that the average number of bits. So the number of bits will be at most n divided by gamma squared. Okay, so if we can show that this value is non-zero, which means there is a function that satisfies both terms for every age, for every function. So if we have a function that satisfies both terms for all the class, and all those functions have at most n divided by gamma squared bits, this means that there must be at most 2 to the power of n divided by gamma squared function like this, which is our covering that we want, gamma cover. Okay? So this is the proof idea. So we converted probabilistic issue into existing problem. Okay. Okay, and now I want to let's see some example for a linear function class, and I want to use this example for 2 reasons. First, because we're going to use it later on. And second, because I think it can help understand better the definitions, although it seems that you're pretty okay with them. And so let's H be the linear function class with vectors of bounded norm of 1. And we want to create a compressor for this. So what we're going to do, so let's create for each function, for each vector, let's define the random variable, which is only the vector with only the I element is given and the rest is 0. Okay, so it's a vector that have only the I element with probability Pi, which is Wi squared. Okay, so it's a random variable. Every time we get only one index on one element, and the rest is 0. Okay, so we can easily show that the expected value is indeed, it is an unbiased estimator because the P reduced. And the variance also, it's bounded by the norm of X squared. Okay, so what we've got that W8 is indeed an estimator for W. So, okay, this is one part, but we want to show a compression, so we need to encode it into bits. So how many bits required to encode each event? So note each event is a sparse vector, so we can somewhat encode it smartly by just encoding which index is not 0 and the value of this index. So okay, to encode the index, we need log the bits because we have the dimensional vector. But how many bits we need to encode Wi? Because Wi number may be bounded by 1, but it can have infinite number of digits after the decimal. So we cannot use just a constant number of bits. So let's do the following trick. Assume B1, B2, etc. is the possibly infinite bit representation of Wi. That is Wi is the sum of Bj times 2 to the power of minus j, because they are all smaller than 1. Okay? And let's define the random variable B hat to be the j bit with probability 2 to the power of minus j. Okay? So nicely, the expected value of B is just Wi, so it is indeed unbiased. And this is bounded by Wi itself, which is even bounded by 1. So we get one estimator. And how many bits did you use for each event? Only one bit, right? Because we encoded only the j bit for each event. So all in all, we get one compressor for Wi. So we don't not do just that we a constant number, we even can do that with one bit. So this was the example, and of course we can from that assume we need log B to define the index, and then X because this is the variance, but this is the overall idea. And some more ideal calculus that we'll use further. So we'll see 4 results. So the first one we already know that we can, so let H be a class with an ideal of n. So we can get a compressor with a small variance by pairing more bits. And the second one is that we can add two functions, some two functions, so two classes, and getting an ideal which is the sum of both. The third one is composition with linear functions, so it's similar to what we've seen, just with it's an extension of that. So first, you want a composition with already with a class that already has an ideal. Second, with don't just use vectors, we use any we manage to go into any matrix. And third, that we are not bounding just the norm of the class. We can bound the distance from some initialization, which is usually what happened in the neural networks. So this is the extension, but the results are more or less the same. We can show that we can have an idea that it's approximately an order of n up to some additive values regarding logarithmic terms. Sorry, avoiding not including logarithmic terms factors. And one nice result of that is that the width of the vector of W, I mean, it doesn't matter how many what is the dimension that W that the mass of W is. And our result is still somewhat width free. It's independent of the width term, except for logarithmic factor. Okay, so this is a nice result. And the last one is, so this one was composition with linear function. The second one is composition with nonlinear function. So we know how to compose the class with nonlinear functions with subset of nonlinear functions which are smooth enough. The definition is below, without adding too much to the asymptotic bound, except for logarithmic factors. Okay, so yeah.
Do a lot of this analysis they were the covering enough, right? Like in the linear case, you can also bound the covering number directly.
Mm-hmm.
And these ones, I mean, what specifically do you gain from working with ADL instead of just trying to bound the covering number?
Okay, so
this, like, there is an equivalent of this now for covering numbers, or?
okay, so this is a great question because this is the topic of our next problem. And one, okay, yeah.
The dimensions here, the term b plus b squared, like b squared sort of has units.
Yes, because we bound the.
So how b plus b squared has like, I'm just, d is sort of unitless and b has a unit, so you have somewhere bounded next to them.
Yeah, we consider, because if we, for example, use the dimensional cube, so the x is bounded by square d. So it's somewhat related. We usually consider b squared to be as if it is d. This is what usually happens. Okay, so that's why I didn't want to avoid it here. But yeah, it's a good question. And regarding your question, we have, as we cannot go from, we can go from ideal to covering, but we cannot go backward from covering to ideal yet. I know, no, actually. So we need to show all of them for ideal in order to get the following bound, which I'll explain later, and which is our next topic. What we can do with that, what we can do with ADL, so application in deep learning, and I noticed today that this is also an ADL. You have a question?
No, sorry, I think I understand.
Okay. So what is it good for? Why am I talking with you about this new concept? What is it better than covering number? So let's see some of applications. So assume a neural network. So a neural network is just a composition of linear functions and nonlinear activation function, which is the activation function will be known by rho, with some element-wise Lipschitz function like ReLU, sigmoid, etc. And we allow bounding the distance from initialization by some R, which is empirically there are lots of evidence that usually a neural network is not going far from its initialization, and what's okay, and the dimension of the vector W will be d times d just for simplification. Of course, we can extend it to any width, but for our talk, we'll have all will have the same dimension. Okay, so we want to bound the generalization of neural network, and usually the theory is far more okay, from practice results, and more specifically, the class uses an order of d squared parameters. So some naive multi-dimensional results show that epsilon squared must be an order of d squared, the number of parameters divided by m, which is in practice very far from the real result. But we're smarter because not just using any class, we are using the bounded case, the one with bounded norm. So can we say something better? And so there were a lot of works about this case of norm-based bounds, but all of them managed to give a result that if you convert it to our scenario, it's still linear. It's still linear in the number of the parameters. And our result show a sublinear dependency of the parameters. And not just that, we can also show that this is somewhat tight, except for logarithmic terms, and except of some asterisks that we cannot show this proof for any function, but rather the set of smooth enough functions that we introduced before. So it's still not the all set of functions, but we can show that there are some functions that for them we can show a tight bound with sublinear amount of bits. So this is the result, which I don't know if one could use the covering number. I didn't see any work that uses covering number to have this bound. So this is why our idea, I don't know if it's better, but it works. Okay, so this is what's the main idea of using the ADL. You get a sublinear result, yeah?
What is the design of the approximation? How would the approximate?
What? What do you mean?
This whole thing is about approximating the.
Yeah.
So what is the trade-off between how would you approximate it?
So,
Or you just find the best approximation that gives this bound?
so yeah, it's just show there is an approximation. I can't show you like the lower bound that this is the best approximation that there is, but we managed to show one approximation that do that. So this is what we got, and so this is more stating better what I just said. So we can have a bound which is sublinear, and the proof is actually you've already seen it. Is just using a composition of linear and nonlinear functions, and just a small note, the result is working only for, currently we managed to show it only for small enough functions, and this does not contain value, although it is very widely used, but it works for some approximation of value, so we can show it for that, but we cannot show it for value itself. Okay. So this is our upper bound, and for the lower bound, we can show that there are dr squared and order, sorry, of dr squared samples that strongly shatter the class. So strongly shatter is similar of shattering in VC dimension, except with a margin of 1, because remember we're working on the real valued case. And this lower bound is indeed include value. So for the lower bound, we can include value. And if we can shatter with the squared, so it means that the sample size must be at least this order, or at least there are some cases in the worst case scenarios that uses this number of samples. Okay, and small one note that I've already said, but the set of upper bound functions and the lower bound functions are not all of them the same, but are different sets. So we know that there are some discrepancy in our upper and lower bound. So this is still an open case, but there are some functions that do satisfy both, and for them, of course, we have tight bound. Okay, yeah.
What is the depth scale for them?
What do you mean?
Like,
The depth of the network. So D will be I didn't write it. Okay. So if we use different width, so D will be the maximum width, and
the depth. So for the, I
No,
mean, you don't show any dependence in depth, or it's in the.
okay, so yeah, there is some depends on the depth, and we didn't put it in the, or we assume the depth is fixed, but yeah.
For the lower bound, it would work for like.
Yeah, I ignore depth, but yes, it is of course a factor in the equation.
Let's say the lower bound holds for like 1 or, yes.
Yeah, for two layers. One?
1 hidden.
Oh yeah, one hidden layer, yeah. Okay. And so okay, so this is a nice result, I think. And okay, so this is the proof. I will not go over it, I think. My time will be end. Okay.
If I understand correctly,
Yeah.
when you constructed it, the fact that in reality we don't have the space of hypothesis, but finite representation. I mean, we work in computers; they have a finite set of bits to represent every number. So, if I understand correctly, it doesn't matter to you.
The sticky trick?
What?
You mean?
No,
What you call it? Yeah.
It's 32, I don't know, whatever bits for per number. We
Yeah.
are in a finite thing. Crazy big, but still finite. So
Mhm.
if I understand correctly, you can't leverage it very much because it's decreasing. It's what happens after the 32nd bit is negligible probability, so it doesn't
Yeah.
affect the. But for the smoothness,
Yeah.
okay, I mean the difference between value and let's say the smooth function we don't want plus the x. If you have finite number of bits, but everything is finite number, not only.
Mm-hmm.
So, is there a way, or I don't know, is there a result that concerns what happens if the
So you need
sensitivity is bounded in any way?
Yeah, so you need a very rough sensitivity for that, I think. But well, first we've seen that using bounded number of bits, we don't care if it's infinite because we can still bound it. But using, although maybe we can avoid sometimes the logarithmic dependence of m if we use constant number of bits. But also you need a very rough approximation, yeah, to get that still. But yes, the problem of value was very very bothering us. Thank you. And for the third application, the third result, for the second application, we wanted to see, okay, maybe we couldn't show type result for any element wise Lipschitz function, but maybe for a simple case of two layers, we can say something nice. So indeed, the following lemma states that at least for two layers network, we can show the same bound that we want for any element-wise Lipschitz function. So this one does include value and whatever other function that you use. So for two layers network, we can show a tight bound. And one more interesting notice is that this result is width-free. So we don't care what is the width of the function, what is k. The bound is the same, not even by logarithmic factor. So it's width independent. And I want to show you the proof of width for two elements first, because I think it's a nice construction. And second, because I want you to see if you can catch how we avoided using the width, how to get a width-free result. Yeah, question.
This might be unrelated, but empirically, then you see that the weights don't change much, only when you have a very deep network. Right?
Yeah.
So if you have only a shallow network, like only one deep layer, then the bound of all would be much higher than one of the deep, right? So this will still, it's like expanding the complexity here. It's still good, right?
So yeah, so we don't know much about R, so we just use it as a parameter. But yes, it could. So you'll see later. I'm giving you spoiler that R suffeg absorb to itself some of the reach. Okay. But yes, it's an interesting question what R is for two layers and what we can say about R. Yeah.
Just to compare this to the previous result. In the previous result, you didn't have k, but k was just equal
To be
the same number.
Yeah.
And if you took k to be a different number in the previous result, you get a dependence on b or k.
Oh yeah. So when you use several when you compose several function over the other, then you have to use the second parameter because it becomes the input of the next layer. Okay, but you can avoid like the last output.
But you get dependent on the higher one.
Yeah, on the higher one. Yeah.
K R squared. If k is larger than this, it's
Yeah.
R squared instead of Q.
Yeah. Okay. So because we need the input is so there is a dependency in the input. So every layer has an input which is the output of the previous one. So that's why over there k is important, and here we can make it with 3. And okay, so this is the proof. Assume, okay, so the proof will have two parts. So the first part, I assume the width is 1. We have only one neuron. Okay, so this is, of course, this is good reason why we get good free result. And this is actually the estimator that we use. So see that is a telescopic sum of some weird things. So each one is reduced with the other. And what is WI? So WI is just a compressor, an estimator that uses more and smaller variance that decrease exponentially. But in return, we need to pay more and more bits. Okay, so we get smaller and smaller variance on one hand, but you need to pay a lot of bits. So how can we make this? How can we control it? So we could try it using another variable, vi, that is have an expectation of 1. So an expected value, we don't care about it, but it is getting smaller and smaller and smaller probability as I increase it. So with small probability, we pay a lot of bits, and with high probability, we pay small amount of bits. Okay, so this is the idea. And of course, the last term, what we call the error, is just stating the exact value. So here we need to encode the exact, the entire value W. Okay, so we need to encode all of the parameters, but of course, as I said, we do it in a very small probability. Okay, so again, some compression bound, we can show that this variance, we can bound this variance and to push it to see that this value has an ideal of times the norm of W squared. And of course, it's width-free because we had only one neuron. So let's do that. Let's now make. Let's bring back all the neurons again. Okay. So a neuron is just a linear function. So we can and then nonlinear activation function, and therefore we can just concatenate them over each other for each neuron. We will create the same estimators that we had before, which cost d times the norm of this neuron, of this weight. And it's very easy to see that this is indeed an unbiased estimator. But more importantly, note that rho is element-wise. So the rho of every of the function of the concatenation function are independent, because for each value we create an independent set of parameters, and rho is element-wise. So the variance is therefore the variance of the sum of independent random variables is the sum of the variance, which is just still 1. We keep it still the same variance. So we managed to not increase the variance, even though we would use, I don't know, infinitely many amount of neurons. Okay, so this is nice, but what can you say about the number of bits? So for this, we do need to pay something that is costly, like in the weeks, but note that if we sum over k, and each one has a compressor that equals to the norm of this vector, then we just get a Frobenius number, Frobenius norm, sorry. Okay, so this is what I said, that we hide actually the root in the Frobenius norm. Okay. So we managed to get width-free result, or at least implicitly width-free. So the question is, does it necessary to have? Of course, what helped us to get this? So because rho was element-wise, so we managed to not increase the variance. Okay, so is being element-wise the necessary property of the function? So the following result shows that yes, if rho was not element-wise, then there are at most, sorry, if rho was not element-wise, then you cannot get a width-free bound, upper bound, and we show it by showing a set of samples that goes with the width that can strongly shatter the class. Okay, so there is, I'll say it again, there is a one Lipschitz, but not element-wise function, activation function, that using a number of k samples, we can shatter the class, and therefore we are not becoming width-free anymore. And And the proof is very simple. You just pick at random k vectors, k samples, and 2 to the power of k matrices, and you can show that the probability that all of them, the result of the multiplication for each with each, is just resulting in very far away points, or the points are very far away from each other. And therefore, you can just create a function, smart function that remembers all those points, assign each point 1 or -1, depends on what you want, and go from one point to the other by keeping the functions Lipschitz, like somewhat stay Lipschitz, because they're so far away. So, yeah. So this is the idea. So indeed, element-wise is a necessary property to get a free result, generalization bounds. Okay, so to sum up, question, by the way. Okay, so let's sum up. So I introduced you today with the concept of ADL, the approximate description length, which is a tool that I hope you use yourself in your research. And we've seen that this tool can give us tight asymptotic bound with some, of course, asterisks about which activation functions. And that using the research, the investigation of ADL, we got the nice property of element-wise that we can manage to get a width-dependent result, width-free result, sorry, which is also a necessity property. And there are some open questions. Some of them I already introduced before, like, for example, what is R? What can you say about other activation functions? And so forth. But let's see if you have any open questions for yourself. So it's time. Yeah.
You showed basically that the main tool was to approximate your network with some very sparse functions.
Yeah.
But network. More complicated.
The linear part, you say.
The linear part was sparse. I don't know if the rest of it.
Yeah, I didn't show the case for smooth functions. It is actually a bit somewhere.
Okay, let me ask the question.
Okay, yeah. So, okay.
The question is, can you gain something in terms of computation complexity of inference from this tool? Like, can you use these constructions to show that you can, run networks faster? Like, if you would do this with sparse approximation, this is much more efficient. You can do like sparse multiplication much more efficient.
Oh,
right. Counting the number of multipliers.
So
I'm asking if this ADL technique can give you something in terms of, say, I have a network that is this reusable norm is bounded by R. What can I gain in terms of computational complexity?
So I think sadly, if I understand. Yeah.
In the approximation, we have that parameter, so you can make it faster.
Yeah, but since we're using several functions, we can.
Yeah, still. I mean, it boils down to how many
functions we make.
This approximation versus the original. Question. Since
So
not dependent on width, say in the.
So like if gamma is I don't know, constant, that use constant amount of functions, and then it is sparse. Yes, right. So
I mean, this is.
that there is a sparse function. Yeah, nice. Yeah. Okay. Great idea. Didn't thought of it. I need to see like when the width increases, because every time you sum spots of that matrices, but I think it's possible. Yeah, just need to, okay. Other question? Yeah.
I think this is a product lecture, maybe they were about applications doing PhD.
Okay, so yeah, I said at the beginning that I'm going to talk about one project. So for this project, there is some published paper, and the part about element-wise is still unpublished result. And for the model extraction, we have a paper that is up under supervision, and we hope it will be published. And so under review, sorry, under review, sorry. Yeah, and yeah, so this is.
Hopefully comes soon.
Yeah. No, okay. So thank you again.
Let's take the speaker again. Okay.
Oh yeah. So thank you, Elad, and we'll meet you all today. Next week again at the same room, the original room. Just for today, they asked us to go here. To the, yeah.